Hi, and welcome to the final part of the six-part series on time varying temperature profile of a uniform bar. In this video, we're going to implement the Crank-Nicholson method that we discussed in the last video and plot the temperature profile as a function of time using Google Colaboratory. So let's go ahead and go to the code. This is the code that we wrote in part 3, I think. So if you want to know about that, then you can go to that video and watch it. But we are basically going to use this and build off of it to get rid of the instabilities that we've already discussed by implementing that Crank-Nicholson method. So the first thing that I'm going to do, I already did, was add in this new import. So this will allow us to do linear algebra, since that's what we need to do to be able to implement the Crank-Nicholson method. And the reason why is because we will be using these. We will be using this matrix and vector to implement this in code. So this is just an example, but the matrix is for the bar that we've discussed. This particular bar in this example is only 5 sections, and we can see the 3 diagonals there. And then the vector, which is what our matrix is equal to, so like our right-hand side of the equation, is all of our equations. So we need this import to be able to solve those. And let's go ahead and activate everything. Okay, so this is where we left off in part 3, and now we are moving on. So the first thing that we need to do is specify our initial temperatures, which again, we're just gonna set them equal to 20 degrees Celsius across the bar. So we can do that easily using NP full, and the shape, or like the size of the matrix, is again NX, which is our position increments. So, yeah. And then we'll do the same thing that we did previously and just set each end equal to, we'll do one end, the left end equal, like the first increment, so the left end equal to 50 degrees Celsius, and we'll do the other end equal to 80 degrees Celsius. So again, our outside edges of the bar are at these set temperatures. So 50. And then on the other end, it's indexed at -1, so equal to 80. Okay, so now we need to set up the matrix, and we're gonna call it A. And we will start out setting up the matrix by giving it that upper, main, and lower diagonal. So first thing we'll do is we'll set it equal to 0, as always. And the matrix is going to be 3 by, in this case, 48, because we're doing 50 increments of position and we're excluding the 2 ends from that. So 50 minus 2 is 48. So we'll just do NX minus 2, and it's 3 by 48 because there are 3 diagonals. So yeah. And then we can specify each diagonal next. So for the upper diagonal, that's going to be indexed at 0, 1, and then 1 to the end. And if we pull our picture back up, that is the upper is equal to negative r, so is the lower. And then the main diagonal is equal to 1 plus 2r. So they equal to negative r. And then our main is just going to be 1 to the end. Indexing, I mean. And again, that's 1 plus 2. Oh, 1 plus 2r. And then the lower matrix is going to be indexed at 2 till the last value. So yeah. Oh, excellent. And again, that's going to also be equal to negative r. And we can check that by just typing in A. And that's exactly what we want. And we can see that the first and last values in the upper and so the first value of the upper diagonal is 0, which is good, and then the last value of the lower diagonal is 0, which is good. Okay, so now we have our A matrix, and next we need to supply the B vector, which is the right-hand side of the equation. And once again, it is going to be, in this scenario, sized at 48 because it's just going to be the number of position increments or like slices minus 2. And we will start by setting that one equal to 0 as well. So again, it's all the slices minus 2. And now we can write out what it actually is. So it'll be r times t2 to the end, because yeah, that's the indexing for the first value in the expression, and then it'll be just 1 minus 2 times r times this t value. So and that's just going to be indexed at 1 to negative 1, so like all of the inside, because that's our main matrix. So it's all of the internal values. And then our lower diagonal is just going to be, or not our lower diagonal, but our last part of the expression. And also really quickly noted, obviously the first and last equations of the vector are slightly different, but we will account for that later. So just focus on like the third term, which is what makes it similar to the equation that we've been using this whole time. So it's r times t, and it'll be everything until 2 values until the end. So everything till the end minus the last one. So that's to negative 2. Yeah. So now the first and the last terms need special treatment, like I just said, because they are different from the middle. And the first term just adds on a like r times the t0. And then the last term just adds on r times the last value of temperature. So we can just directly say that b index at 0, so the first b value is going to be equal to the b value that we already came up with plus what's added to it that's different from the rest. So again, that's r times t0. And then the same thing for the last p value. It's just going to be what we already got plus r times t at the last value. Okay, so let's graph our initial conditions, and then we can basically iterate what we just have done and get our final product. So enter, and we'll just call it fig2. Call the other one fig. Make subplots. We only need one row and one column. And it's going to be a scatter plot again. And the x values equal x. We have that already. Yeah, because x is each slice of the bar. And then the y values, t, and we'll call this one initial as well. Okay, so this is what we got at first. It looks similar to the first plot that we had previously in part 3, but now we're going to iterate it basically the same way we did in part 3. So we're basically repeating part 3's coding video, but with the Craig-Nicholson method and using, I guess it's slightly different, using these matrices and stuff. So it is generally the same process, but yeah. So we can iterate using a for loop and that import that I had at the very beginning that lets us do the linear algebra. It's a function called solve banded, and I actually have a page pulled up of it right here because it is able to solve a banded matrix, and this kind of looks like what we have because the stars are zeros. But anyways, so for I range, and it'll be nt plus 1. And all we have to do to iterate is just basically plug in what we just did. But first we have to, for all of the internal temperatures, set that equal to the solve banded function and using A and B. So temperatures, all of the internal slices, so from 1 to -1 is equal to solve banded. And this is just going to be 1, 1. And then it asks us for both sides of the equation. So A, our matrix, and then B, our vector. Yeah. And we can go ahead and just look at what that looks like. Oh. Yeah, so we can see it here. Okay. And then we can just copy and paste what we have for B below that. That's a lot to rewrite out. And then also, just like in part 3, we're going to use the modulo function again, which again just allows us to iterate over many small time increments, but continue to only plot for every 1 second. So I can't remember what we set the number of time increments to, 1,000. So it makes more sense to just plot it every 1 second versus every single point. So again, I can probably just, I'm just going to copy this. Paste it. And it'll be fig 2. I think. I'm not going to do this. So I'm going to eat the go. Scatter. What do we have on here? X equals X, Y equals T, then the name. Yeah, okay. X equals X, Y equals T, and then the name is just going to be function I S. That should be good. Okay. Great. And then we can see all of the time increments here on the side. Did I? Yeah. Okay, so this 6-part series is officially complete. Again, in part 1, well, I won't run through it. You can watch it if you want, but whatever. So this is our official code and graph of the time varying temperature profile of a uniform bar. Thank you for watching.